We now go on illustrating, understanding, describing, and interpreting the graph and solve problems involving polynomial functions. But in this video, we focus on illustrating and graphing. So to illustrate polynomial functions, these are the things that we are going to do. So number one, we are going to define what polynomial functions are. Number two, we are going to identify when a function is a polynomial, when is it not a polynomial. And number three, we are going to identify the characteristics of polynomial functions. Let us now go to the definition of polynomial functions. So a polynomial function of degree n is a function in the form f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 and so on until a sub 0, where n is a non-negative integer and a sub n minus 1, a sub n minus 2, and a sub 0 are real numbers, and a sub n is not equal to 0. We notice that the notation of a polynomial function is quite complex, but we are going to simplify that later on. Let us now focus on the conditions when a polynomial when a function is a polynomial, or when is it a non-polynomial. So these are the four conditions that we have to look for. Firstly, if it has a negative exponent. Actually, if it has a negative exponent to a variable. Notice that our negative exponent here is to a variable, or to the variable x. Therefore, we have a negative exponent to a variable. The function is non-polynomial. Next, if we have a variable in the denominator, as you can see, we have here an x in the denominator. So therefore, that is a non-polynomial, or that is not a polynomial. If you know your laws of exponents, you know that these two morph into just one, the negative exponent and the variable in the denominator. Next, if the variable has a fractional exponent, so we have a fractional 1/2 exponent to a variable x, so this is also a non-polynomial, and we have a variable under the radical sign, that is also a non-polynomial. And if you know your laws of radicals, you know that these two also morph into just one. But if you are looking for specific things on your polynomials, then these are the four conditions that we are looking for to tell that a function is a non-polynomial. Now, what are the different characteristics of polynomial functions? So this is the complex notation of a polynomial function, and we have labels to identify the characteristics. Firstly, the degree of the polynomial. We should consider and always keep in mind that this notation is a polynomial function in standard form. So the degree of the polynomial is the very first exponent if the polynomial function is in standard form. Now, the leading term is the the leading term is the very first term, and its coefficient is the leading coefficient. Now, the very last term, the term without the variable, that is the constant term. Now, given this polynomial, let us identify its characteristics. Firstly, what is the degree of this polynomial? To identify the degree of the polynomial, we should check first if it is in standard form. How do we know if it is in standard form? If it is in decreasing order of exponent. Obviously, it is in standard form because we started with an exponent 3, and then we had an exponent 2, and then an exponent 1, and then we have our constant term here. So this is in standard form. So the very first exponent, that is our degree. Or if the function is not in standard form, then just look for the largest exponent, and that is the degree of the polynomial. The leading term is the very first term when the polynomial is in standard form. Since our polynomial is already in standard form, the very first term, so that is 3x cubed. That is our leading term. Our leading coefficient is the numerical coefficient of the leading term. So our leading coefficient is 3. And our constant term is the very last term, the term which does not have a variable. So the constant term is -3. There are instances when polynomial functions do not have constant terms because all terms have variables. That can also be. So these are the things that we need to do to be able to illustrate polynomial functions. The more complex task for us is to graph these polynomial functions. These are our considerations in graphing polynomial functions. First is the x-intercept, or are the x-intercepts. By definition, x-intercepts are points where the graph touches the x-axis. How do we find x-intercepts? So we have to solve for the roots or zeros of the polynomial equation set up. So we are going to be given a polynomial function. So we set up a polynomial equation, let y be equal to 0, and solve for its roots. Second, the behavior of the graph towards the x-intercepts. In our previous discussions, we talked about multiplicity, and we discussed the importance of multiplicities towards the graph. So this is where that certain importance comes into play. So we have a multiplicity of 1. The behavior is cross. This is the figure. This is how your graph will look like towards an x-intercept. So we have a bounce right here. This is what your graph will look like towards an x-intercept if you have a multiplicity of 2. And tangent for a multiplicity of 3. This is what it looks like when you have a multiplicity of 3. If you have a multiplicity of 4, you go back to a multiplicity of 1, and so on. Next is the y-intercept. So by definition, the y-intercept is the point where the graph touches the y-axis. So it's essentially just the constant term. So if we let x be equal to 0, then we are just left with the constant term. That basically is just the y-intercept. Now, the end behavior of the graph has something to do with its leading coefficient, the degree. So we can identify the end behavior. If the leading coefficient is positive and the degree is odd, this is the end behavior of our graph. If the leading coefficient is positive and the degree is even, this will be the end behavior of the graph, and so on. Number 5, find the number of and specific turning points. So how do we identify the number of turning points? So that basically is just the degree minus 1. So the degree minus 1, that is the number of turning points our graph will have. But how do we find specific turning points? So identify the midpoint between x-intercepts. This is important. To identify the midpoint between x-intercepts, that will be the x value of the turning point. And then plug in the place of x on the given polynomial function and solve. So that will be the y value of the turning point. So we will have now an ordered pair with an x value and the y value. So we can now solve, or we can now identify the turning points. Note, a bounce is considered a turning point. So these are our 5 considerations in graphing polynomial functions. Let us now go on and try to graph a polynomial function. So let us try to graph f of x, which is equal to x cubed plus 3x squared minus x minus 3. Our first consideration, the x-intercepts. So I will write here, x-intercepts. How do we find the x-intercepts of the graph? Let's go back to the definitions. Solve for the roots of the polynomial equation set up. So we will set up a polynomial equation. So this could be x cubed plus 3x squared minus x minus 3 equals 0. This is now our polynomial equation. Let us now find its roots. To find the roots of this polynomial equation, we will have to use the rational zero theorem. So we have to identify p-values and q-values. So the p-values are the factors of the constant term. So we have a positive, negative 1, and a positive, negative 3. Q values are the factors of the leading coefficient. So we have a positive, negative 1. Let us now identify P over Q values. P over Q values. So we will have here positive, negative 1, and positive, negative 3. Let us now use our synthetic division to try and solve for the roots or zeros of our polynomial equation. So I'll perhaps try 1. And then copy all the numerical coefficients of the terms of the polynomial equation. We will have 1, 3, negative 1, and negative 3. Hopefully, the remainder becomes 0. So we have to bring down 1 times 1 is 1. 3 plus 1 is 4. 4 times 1 is 4. Negative 1 plus 4 is positive 3 times 1 is 3. Negative 3 plus 3 is 0. Therefore, positive 1 is one of its roots, which represents the factor x minus 1. And now let us compose our depressed equation. What is now our depressed equation? This will be x squared plus 4x plus 3. Why is it an x squared? Because we are given a cubic polynomial equation. And one of the factors is of degree 1. Therefore, if we subtract 3 minus 1, we get 2. That is why our depressed equation is of degree 2. So this will be equal to 0 and can be factored out. Factors of which are x plus 1 and x plus 3. Now that we have all our factors, we can factor our polynomial completely and identify its roots or zeros. So I'll just copy this. So I won't write it anymore. I'll paste it here. And let us factor this polynomial completely. So the factors are, firstly, we have x minus 1 second factor, x plus 1, third factor, x plus 3. The arrangement can be a different arrangement. Let us now observe our factors. I mistakenly wrote x plus 1 instead of x minus 1. Now, let us observe the factors. Do we have similar factors? No, we don't have similar factors. So we won't have any multiplicities. All of our factors just have a multiplicity of 1. Therefore, we can now apply the zero product property, equate each factor to 0. So x minus 1 is going to be equal to 0. So our first x value is positive 1. Equate the second factor to 0. So that is x plus 1 is equal to 0. So our second x value is negative 1. And equate the third factor to 0. So x plus 3 is equal to 0. So our third x value is negative 3. So what are our x-intercepts now? So our x-intercepts are points. Therefore, our x-intercepts are 1, 0, negative 1, 0, and negative 3, 0. So we have now identified the x-intercepts. Let us now go to our second consideration, the behavior of the graph towards the x-intercepts. Identify the multiplicity and the behavior, which is cross bounds or tangent, which are cross bounds or tangent depending on the multiplicity. But we have identified that we have x-intercepts that have multiplicities of 1 only. Therefore, in each of these x-intercepts, our graph will only cross. So we have a cross here, we have a cross there, and we also have a cross here. So that is our second consideration. How about our third? Find the y-intercept. So that's essentially just the constant term. So if we are going back to our polynomial equation, we have here negative 3. Therefore, the y-intercept is 0, negative 3. Next consideration, the end behavior. So we have to identify the sign of the leading coefficient and the degree of the polynomial to identify the end behavior. So if we go back to our polynomial equation, we have a positive leading coefficient and an odd degree. So what is now the end behavior? So the end behavior of our graph is going to be positive odd. So we have here positive odd. That is our end behavior. I'll just copy this and paste it here. This will be our end behavior. Last consideration, turning points. So identify the number of turning points and specific turning points. So the number of turning points is degree minus 1. So number of turning points. Degree minus 1, so we have 2 turning points. How do we identify those specific turning points? So identify the midpoint between x-intercepts and plug in the place of x on the given polynomial function and solve. So it would be easier for us to identify the midpoint between x-intercepts if we graph them now. So let us now go to our Cartesian plane and have our axis. So this will be our x, and this will be our y. Let us now plot our x-intercepts. The x-intercepts are 1, 0, negative 1, 0, and negative 3, 0. So we have 1, 0, negative 1, 0, and negative 3, 0. So let us now identify the midpoints between x-intercepts. So between these two x-intercepts, the midpoint is right here. But what is this? This is negative 2. So I will remember, one of the midpoints is negative 2. How about these two x-intercepts? The midpoint is right here. That's 0. So those are our two x values, negative 2 and 0. What we want to do is to get our polynomial equation here. So I'll paste it here, perhaps somewhere here. And then, instead of x, I'll plug in negative 2. If we do that, so we'll have here negative 2 cubed plus 3 times negative 2 squared minus negative 2 minus 3 equals 0. So we have here a negative 8 plus, this is 3 times 4. This is a plus 2. This is a minus 3 equals 0. So we have negative 8 plus 12 plus 2 minus 3 equals 0. Combine terms with the same signs. So negative 8, negative 3, that's negative 11. Then we have 12 plus 2, that is 14. Don't have here an equal 0. I'm sorry about that. So we won't have equals 0 here. Instead, actually, we will have on the other side f of x, which is just y. So equals here. So we have 14 minus 11, that is going to be a 3. So that's f of x. F of x is 3. That is a y value to an x value of negative 2. Therefore, one of the specific turning points is the x value is negative 2. The y value is positive 3. Next, so we have f of x is equal to, I'll just copy this, paste it here. Instead of x now, I will write 0 because that is one of the midpoints. That's the other midpoint. So essentially, this is just going to be 0 cubed plus 3 times 0 squared minus 0 minus 3. And we all know that we can cancel everything here. And we are left with f of x equals negative 3. Therefore, the other turning point is 0, negative 3. We have now completed the data that we need to graph this polynomial function. I'll just copy this and paste it here so I can be properly guided when I am graphing our polynomial. So the x-intercepts are already plotted. We have to cross on those x-intercepts. The y-intercept is not plotted yet, so we will plot our y-intercept Our y-intercept is 0, negative 3. So here is our y-intercept. The end behavior is going to be like this. So we'll have something here going downwards and something there going upwards. The number of turning points, we have 2. Specific turning points are negative 2, 3, and 0, negative 3. So negative 2, 3 is somewhere here. 0, negative 3 is somewhere there, just the same as our y-intercept. And now we are ready to graph. So we are going to have something going down here because that is our end behavior there. And then we are going to turn here because this is a turning point. And then we are going to cross here because that is the, so we cross at 1, 0. We cross at negative 1, 0, and we cross at negative 3, 0. And then we turn here, and then we cross again on that x-intercept. And that is the graph of our polynomial function.